Welcome to Variational Principles and Lagrange's equations. Today we are going to be discussing some techniques on the calculus of variations. We wish to find a curve for which a given line integral has a stationary value. Namely, we are looking for the functional f for the function y of parameter x between the points x1 and x2 with y dot being the derivative of y with respect to the parameter x. For all the paths, the values of the function at the endpoints of the interval, so the values in x1 and x2 are equal to y1 and y2 respectively. And we seek the line integral j, given by formally given by the expression here, having stationary values relative to paths infinitesimally close to the correct path y of x. This assumes that the parameter x is unidirectional in going from x1 to x2. Otherwise, the integral must be broken into unidirectional parts and the results added algebraically. So this is a subtle condition that needs to be kept in mind when discussing the variational principle for functions that may not be unidirectional in the given parameter, so they may not vary in a single given direction. For a particular subset of paths labeled by an infinitesimal parameter alpha, the variation will be zero. This set is labeled by y of parameter x and parameter alpha, with y of parameter x and alpha equals 0 representing the correct path. For functions zeta of x vanishing at the endpoints, the parameterization of these functions is given as follows. So y of x and alpha is going to be equal to y of x and 0, which is the correct function, plus the parameter of alpha multiplying the function eta of x, which vanishes at the endpoints. Y and eta are both assumed to be well-behaved, continuous, and differentiable up to the second order between x1 and x2. And as such, the line integral j as a function of the parameter alpha is given by the expression here. So we've simply made it explicit that y and y dot depend both on x and on alpha. And the stationarity condition will read that the derivative of this integral with respect to alpha, when the parameter alpha is equal to 0, must also be 0. So this derivative vanishing means that the integral is stationary for this particular function. Now, if we just differentiate with respect to alpha, we carry out the operation under the integral sign. So we're just, by applying the chain rule, we take the derivative of f with respect to y, and then the derivative of y with respect to alpha, plus the derivative of f with respect to y dot, and its derivative with respect to alpha. But since x itself is independent of alpha, we do not have a third term containing that the partial derivative of f with respect to x and then the partial derivative of x with respect to alpha. Now, regarding the second term here in particular, it is obvious that the second derivative here can be expanded as follows. So this is the second order derivative of y with respect to x and alpha on the one hand. And then if you look at the total derivative with respect to x from this product of functions, then by the chain rule, this is equal with the derivative with respect to x of the first factor plus the derivative of f with respect to y dot and the second order derivative of y with respect to x and alpha. So this is exactly the factor here and the term here, and as such I can write this one as this total time derivative here minus this term. And now if since I have a total not time derivative, sorry, so derivative with respect to x. So now if I have this derivative under the integral sign, it means that what I need to evaluate is the product of these two derivatives taken between the between the endpoints, but I know that in particular this derivative is just eta of x, and the condition is that eta of x vanishes at the endpoints, so this thing is 0, and what I am left with is, with a minus sign in front, the term here. And then once again, by applying the fact that the derivative of y with respect to alpha is eta, it follows that the derivative of j with respect to alpha is given by the expression here, where I have factorized the derivative of y with respect to alpha. And by requiring the stationarity condition, so if I want this derivative to be equals to 0, I obtain the result here. So we have this coefficient multiplying the derivative of y with respect to alpha for alpha equals 0, integrated from x1 to x2 must vanish. The derivative of y with respect to alpha is a function of x that is arbitrary except for continuity and endpoint conditions. In the case of equation 2.4, this function is precisely eta of x. The fundamental lemma of the calculus of variations states that if the following integral vanishes, for all arbitrary functions eta of x continuous through the second derivative, then m of x must vanish identically in the range x1 given by x1 and x2. The reason is easy to understand. If we pick eta of x, for example, as a Dirac delta function, vanishing over the entire interval except the vicinity of an arbitrary point, then m of x must vanish everywhere. As such, the stationarity of j implies that the coefficient within the integral must vanish, and for a one-dimensional general problem, we will refer to this as the Euler equation. And we will define the derivative of y with respect to alpha when alpha equals 0 and multiplying the differential of alpha as delta y, which is the infinitesimal departure of the varied path from the correct path y of x at the point x, and thus corresponds to the virtual displacement introduced in chapter 1. And with this definition, we can then we can apply it uh, to the variation of the line integral j, and then we can write the stationarity condition. We can expand it as follows: delta j is equal with the expansion here, and this has to be equal to 0, which is equivalent with saying that this coefficient must vanish, and thus the function f must satisfy the Euler equation. Delta stands for the manipulation of parametric families of varied paths. In the following, we will discuss several basic applications of this result. The first example we are going to study is the shortest distance between 2 points in a plane, where the length element is given by the Euclidean distance, so it's the square root of dx squared plus dy squared. And then the line integral is just given by the integral from x1 to x2 out of the line element where we choose dx as the parameter. And as such, the functional which interests us is the one given here, is the square root of 1 plus y dot squared. And we apply the Euler equation to it. So the derivative of f with respect to y is obviously 0. The derivative of f with respect to y dot is the one given here, and from the Euler equation it follows immediately that this quantity has to be constant, because its total derivative with respect to x must vanish, but this can only hold if y dot itself is a constant. And if y dot is a constant a, it means that y is a linear function of x. So generally it has the form a times x plus b, which is just the equation of a straight line. And a and b are determined from the conditions which require that at x1 the value is y1 and at x2 the value is y2, so the fixed endpoints. Such curves are generally called geodesics, so the curves which give the shortest distance between 2 points in any given kind of geometry. As a second example, we will look at the shortest distance between 2 points on a sphere. The line element in this case is given by the radius a of the sphere multiplying the square root, which involves the differentials of the polar angle and of the azimuthal angle. And if we take the polar angle as our parameter, then we obtain the functional f given here. And we need to construct the Euler equation for f depending on phi and phi dot. The derivative of f with respect to phi dot is the one given here, and as the derivative of f with respect to phi vanishes, it means that this quantity needs to be a constant, which I've simply called b. And then if we solve this being equal to b for phi dot, then we can integrate phi immediately to obtain exactly the result here. To obtain a closed expression from this formal result, we can use the change of variables u being equal with cotangent of theta to get to the expression here. And then we can once again use the change of variables u being equal with this coefficient depending on a and b times the sine of v, which ultimately leads simply to fi minus phi 0, which is just a constant being equal to v. And then we simply backtrack for the variables, so we write v as a function of u, and then we write u as a function of theta, and then we convert the resulting expression from the spherical coordinates to the Cartesian ones and find the result here. So z is equal with a function of x and y depending on the parameters a, b, and phi 0, and this is simply the equation of a plane passing through the origin, which is the center of the sphere. So this proves that the shortest distance between 2 points on the surface of a sphere is a great circle, which is a circle having its center at the origin of the sphere. Another kind of problem that can be solved with the calculus of variations is the problem of the minimal surface of revolution, which is the following. Given a curve between the pairs of points x1, y1 and x2, y2, which is rotated around the y-axis, for what shape of the curve will the surface of revolution result in a minimal area? First of all, a strip of the area is given by the length x times the Euclidean length element, dl, and this needs to be rotated around the y-axis, so it gets multiplied with 2 pi. And since we know the expression of dl, this is simply the expression written here. So it's 2 pi times x times the square root of the length element using x as a parameter. And as such, the total area of this surface is just 2 pi times the integral of this expression from the initial value of x to the final value of x. And then the functional f is simply x times the square root here. Now if we write down the Euler equation for the functional f, its derivative with respect to y vanishes, and as such its derivative with respect to y dot needs to be a constant. So x times this ratio needs to be equal to a constant a, and it is clear from this expression that a is smaller than the minimal value of x, because I have a ratio of y dot over the square root of 1 plus y dot squared, so this thing is larger than y dot. And then with this condition we can solve this equation for y dot, integrate it, and then invert it to obtain x as a function of y, and the result is the one given here. It's a very simple calculation which gives x as the hyperbolic cosine of the ratio here involving the integration constants a and b. The preceding result is the equation of a catenary curve with the parameters a and b determined from the endpoint conditions. The curve scales with x over a, y over a, and b over a, and as such the nature and number of solutions can vary greatly for a given set of conditions. If x1 and x2 are both positive and much smaller than y2 minus y1, the absolute minimum is given by the Goldschmidt solution with the expression here. So what the Goldschmidt solution provides is simply the area of the disks at the endpoints of the surface. So it's the disk of radius x1 and the disk of radius x2, and these are summed up because they are connected, in the case of the Goldschmidt solution, by a degenerate straight line between the centers of the disks. This is a discontinuous solution, and such solutions are not suitable for the variational problem. Therefore, there are restrictions in the derivation and meaning of the stationarity condition. Now, for the catenary problem, we are going to assume the particular symmetric case where x1 is equal with x2 and y2 is equal with minus y1 and is considered to be greater than 0. Then, because the hyperbolic cosine is an even function, it will follow immediately that x is equal with a times the hyperbolic cosine of y over a, so the constant b has to be 0, and then this result can be converted to a single transcendental equation in the parameters k and beta given by the expressions here, and this equation will completely characterize the symmetric catenary problem, the equation carrying the label 1. Now, for small values of the argument beta k, equation 1 has the Taylor expansion given here, and this is just a quadratic equation in k, which has the following two roots. So notice that if beta squared is less than 1 over 2, both roots are real. But if beta squared is greater than 1 over 2, then the roots are complex, and as such there is no solution for the catenary problem. While for beta squared equal to 1 over 2, there would be a single solution at k equals with 2. Now, in this case, we are clearly solving the problem not exactly as mathematicians, but rather as physicists. And while this result is remarkably close, we can get a better estimate by simultaneously solving equation 1 and its first derivative for the solution k0. So we just wrote equation 1 for the particular point k being equal with k0. Then we took the derivative of equation 1 and once again wrote it explicitly for the value k0. And then from these two equations, what you obtain immediately is equation number 2 in the variable u being given by the product between beta and k0. So u needs to be equal with the hyperbolic tangent of u. This equation is solved graphically. So the function u and the hyperbolic tangent of u will intersect at the point u0, which is approximately given by 1.2. And then from equation 1, for the value of beta times k being equal with y0, we will get immediately k0 being equal to 1.81. So you see it's close to the value of 2, but it's not quite there. And knowing this and knowing the value of u0, we can obtain beta 0 immediately as 0.66. So this would be the critical value of the parameter at which I no longer have two solutions for the symmetrical catenary problem, but rather I have a single solution. And for greater values of beta 0, I will have no solutions because the values of k become complex. And you can see this illustrated here. So what I'm representing is k minus the hyperbolic cosine of beta times k, as a function of k. And you can see in this family of curves that generally I will have two roots for all of these curves up until for various values of the parameter beta until I reach the value of approximately 0.66, where I have a single solution, and then I have no solutions. I can no longer find any roots for this equation. In the symmetrical case, the surface areas of the catenary and Goldschmidt solutions have the following expressions and ratio. So I wrote the surface area of the catenary curve, which hopefully is the one given here. And then the surface area provided by the Goldschmidt solution will just be twice the area of the disk, given by the radius x2. So that will simply be given by k squared multiplied with a squared. And if I take the ratio of these two areas, I should have the obvious expression here. Now, for small values of beta k, I can perform a first order Taylor expansion of S by expanding the hyperbolic cosine, and hopefully the result is the one given here. So what you end up with is 2 times beta over k. But remember that when this product has small values, then k is given by the roots of a quadratic equation, and as such the ratio S has the value here. Now, if I'm assuming that beta has small values, then it means that I can neglect beta squared in the denominator for the solution having the plus sign here. And this is going to lead to the ratio S being proportional to beta squared. And since this number is smaller than 1, we know that at least one catenary gives a smaller surface area than the Goldschmidt solution. So this is always going to be true in these conditions. However, when I reach the point where beta is equal with the beta 0, the critical value, then putting it in here, it follows that S is approximately given by 1.18. So what this means is that at the critical value, the Goldschmidt solution actually gives a smaller surface area than the one provided by the catenary curves. And as a final observation, the problem of a rope of uniform density and indefinite length hanging in a uniform gravitational field between two posts of different heights is formally identical to the problem of the minimal surface of revolution. And this is the case because the length element of the rope is given by the usual Euclidean distance, and an element of its potential energy is simply the gravitational acceleration multiplying the height of the given length element and multiplying the mass element, which is just the density that I assume to be constant and the length element. And as such, the total potential energy is given by the expression here, where the integral involved, the line integral involved, is precisely the one that we have studied for the problem of the minimal surface of revolution. The next problem we will address is the Brachistochrone problem, which has the following statement. Given two points x1, z1 and x2, z2 in a uniform gravitational field of strength g, what is the curve upon which a body of mass m could descend between them in the shortest time? An element of time is given by the element of distance divided by the body's velocity, so the total time is just the integral between the endpoints of the body's trajectory from this time element, and I can obtain an expression for the velocity just from the conservation of energy in a uniform gravitational field. The expression here, assuming that my coordinates are given given like so. So that is x, z is pointing down, and then this makes sense. I can write v as follows, and then the total time tau follows as the integral here out of the functional f depending on the function z, z dot, and the parameter x. I can write the Euler equation for this functional by making use of its partial derivatives and of the total derivative with respect to x here. And the result should be this one. And now the trick is that I can simply multiply this with z dot to formally obtain the integral here, which states that this quantity is a constant, which I will call C0. And with this being equal to C0, then I can solve it for Z dot and invert it. And the result is the one here. So inverting Z dot means that I'm looking at the derivative of x with respect to Z, which is just the square root here. And I can use the additional change of variables dx to dz being equal with the tangent of phi over 2. And then it follows immediately that z is being given by the expression here. And I can take its derivative with respect to phi to obtain the result here. And then I can take the derivative of x with respect to phi by making use of the chain rule of differentiation to obtain the expression here, which can then be simply integrated with the condition that x and z are equal to 0 at the initial point, from whence it follows that the curve has a cusp at the origin and is given by the following set of parametric equations for x and z as functions of phi, with the constant a being equal with c0 over 2. So all of this is extremely straightforward, and then I can solve one of these equations for phi and bring that expression of phi into the other equation in order to obtain the trajectory, which is the cycloid in the boxed expression here. In the limit in which z is much smaller than the integration constant a, then using the Taylor expansion for small values of phi, I can obtain additionally the approximation here for the trajectory written as z being given as a function of x. Now, things play out quite similarly in the case of an initial velocity v0, which is different from 0. The conservation of energy will give the velocity as the following function. So where I've added the additional constant v0 squared under the square root. The time is given by a similar line integral depending on a functional f, which now features this constant. I can once again calculate the derivatives, which allow me to construct the Euler equation for f. And the result is quite similar with the previous one, but it contains this additional constant. So I once again find that a more general quantity is the one which is constant, and I believe I've made this equal with the constant C1. And in any case, following the same steps, so solving this for z dot and inverting it, you obtain the result here. Then you once again make the change of variables here in terms of a tangent of phi over 2, and you will immediately obtain z as having the expression here in terms of a constant b, which is given by this expression, and finally you obtain that x is given by the formula here. So you can already see from these equations that the cusp is located at a different height, which is given by this quantity. But in any case, from the result here and the one here, you can obtain once again the expression of a cycloid. Now the additional parameters x0 and b are found numerically from the condition that I want to have the same I want the trajectory to pass through the same endpoints as was the case in the previous example. And when doing that, you can look at an illustration, as is the one featured here with z as a function of x, where the continuous line represents the cycloid from for a given pair of endpoints for a body falling from rest in a uniform gravitational field, and the dashed line represents the same problem but for a body having the given initial velocity. So what this says is that if I want to launch it from the same point but with an initial velocity being different from zero, it's as if I launched the body along another cycloid having its cusp uh, further up from the original cycloid for the body falling from rest, and the cusp is located at the height given by this value. The last problem that we are going to discuss in this section is the problem of a Brachistochrone through a uniform sphere. So we are to consider 2 points on the surface of a homogeneous sphere of mass m, density ρ, and radius r. The points are separated by an arc length s. We want to find the Brachistochrone associated with these points through the sphere for a moving body of mass m. The force involved is simply the gravitational force given by Newton's law. And we know that this is derived from a scalar potential, which we find by direct integration by considering first the work done on the particle of mass m by the gravitational field and bringing it from infinity to the surface of the sphere, and then the work done from the surface of the sphere to an arbitrary point r prime inside the sphere. And keep in mind that the mass of the sphere as a function of r is a variable quantity given by the formula here for r smaller than capital R, and is a constant outside of the radius of the sphere. And from these expressions, the integration is straightforward and leads to the well-known formula for the potential associated with a homogeneous sphere when moving inside it. So it's an expression for which the gravitational field is essentially harmonic in the radius. It depends on the square of the radius from the origin of the sphere. Then we can employ the conservation of energy and say that the energy at an arbitrary point inside the sphere needs to be given by the energy on the surface of the sphere. And from this we can obtain an expression for the velocity as a function of r, and depending on the radius of the sphere and the gravitational acceleration g, which is given by the formula here. Now, the length element is written essentially in polar coordinates. So I used theta instead of phi to signify that I want to regard it as a polar angle for motion in a fixed plane. And then the total time is given by the time integral, where the differential element is the ratio of the length element to the velocity, and the final result is the one here, where I use the polar angle as the parameter. So it's the functional f depending on r and r dot with the parameter theta. Now I'm going to use a result which I haven't proven yet, just because I wanted to include this example in the list of one-dimensional problems. But it's not something that's overly sophisticated. So given that the functional f does not depend explicitly on theta, we can make use of a general identity called a general result called the Beltrami identity, which states that f minus this quantity, so the derivative of r with respect to theta, times the partial derivative of f with respect to r dot, is a constant which I have denoted with h. And particularly this constant has the expression here. And the reason why I use this is because it is much easier to manipulate the Euler equation for the simplification provided by the Beltrami identity rather than calculating everything explicitly. And now so I have the equation h is equal to this thing, and I solve it for r dot, I will obtain the formula here. Now, as it happens, this is quite specifically, this is the hypocycloid equation for the parameter r0 squared given by the expression here, or equivalently r0 given by r, the radius of the large sphere, minus 2 times a, where with 2 times a being the diameter of a circle of radius a moving inside the larger sphere. And the parametric solutions for a hypocycloid are given in Cartesian coordinates x and y as the following expressions as functions of theta. So it should be the ones here. And from these, we can calculate immediately the derivatives of x and y with respect to theta, which should be these ones. We can calculate x squared and plus y squared and the sum of the squares of the derivatives. Finally, we can write the length element and the velocity, both in Cartesian coordinates. And the reason why I do this is because it is then easier when returning to the integral it's quite straightforward and trivial to calculate the integral in this way. And the immediate result that you will obtain is 2 times pi. So this follows from the fact that the small circle needs to make a complete rotation within the large circle in order to for the particle stationed at the initial point to reach the second point, and it is multiplied by this constant. Now we need to keep in mind that the arc length traveled on the surface of the sphere is the radius of the sphere times the angle theta 2. So this is just the final angle measured at the center of the sphere for the motion along the arc. And this angle is simply given by the ratio between 2 pi times a divided by capital R. And as such, so I can use this expression to find S, and then I can solve it for A, and finally I can write the time as a function only of S, R, and G, and it should be the formula here. And now if we plug in the values of the constant, so if we take R to be equal to the radius of the Earth, we take the arc length to have this specific value, and then we use the value of the known gravitational acceleration and the value of pi, we obtain a total time for movement between the points separated by this arc of approximately 27 minutes. And the maximum depth that is reached is the one given here, approximately 1.5 times 10 to the power 6 meters. And as an illustration, it looks a bit distorted because it's the two axes are not equal. But essentially, if this is the dashed line is the surface of the sphere, then the motion along the hypocycloid between 2 points on the surface is the one described by this arc, which corresponds to the rotation by an angle 2 pi of the of the circle of radius a moving inside, with a given by the parametrizations here and here. So, and summary and as a summary and outlook, we have performed the variation of a line integral and deduced the Euler equation for one-dimensional problems. We have discussed applications including the shortest distance between 2 points on a plane or on the surface of a sphere, the minimal surface of revolution, and the Brachistochrone problem for constant and harmonic gravitational fields. In the following, we will generalize the discussion to multidimensional problems and derive Lagrange's equations from Hamilton's principle. That being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.